Ok, mi hermanillo, mucha huevada. Ya acabó el break de media hora o más y vamos a volver con esta huevada.
Is done. So here's the story. There's an airplane.
Sí, no he prestado atención por un buen rato. Ya, ok. Shishitomaripo. Ah, Shishitomaripo.
More generally, whenever you have a uniform
Whenever.
distribution on your initial sample space, when you condition on an event, your new distribution is still going to be uniform, but on the smaller event that we considered. So we started with a uniform distribution on the big square, and we ended up with a uniform distribution on just on the red points. Now, besides silly problems, however, conditional probabilities show up in real and interesting situations. And this example is going to give you some idea of how that happens. Okay. Actually, in this example, instead of starting with a probability model in terms of regular probabilities, I'm actually going to define the model in terms of conditional probabilities. And we'll see how this is done. So here's the story. There may be an airplane flying up in the sky, in a particular sector of the sky that you are watching. Sometimes there is one, sometimes there isn't. And from experience, you know that when you look up, there's 5% probability that the plane is flying above there, and 95% probability that there's no plane up there.
Okay.
So event A is the event that the plane is flying out there. Now you bought this wonderful radar that looks up, and you're told in the manufacturer's specs that if there is a plane out there, your radar is going to register something, a blip on the screen, with probability 99%. And it will not register anything with probability 1%.
1%.
So this particular part of the picture is a self-contained probability model of what your radar does in a world where a plane is out there. So I'm telling you that a plane is out there. So we're now dealing with conditional probabilities because I gave you some particular information. Given this information that the plane is out there, that's how your radar is going to behave. With probability 99% is going to detect it. With probability 1% is going to miss it. So this piece of the picture is a self-contained probability model. The probabilities add up to 1. But it's a piece of a larger model. Similarly, there's the other possibility. Maybe a plane is not up there, and the manufacturer's specs tell you something about false alarms. A false alarm is the situation where the plane is not there, but for some reason your radar picked up some noise or whatever and shows a blip on the screen. And suppose that this happens with probability 10%, whereas with probability 9%, your radar gives the correct answer.
Right.
So this is a sort of a model of what's going to happen with respect to both the plane. We're given probabilities about this, and we're given probabilities about how the radar behaves. So here I have indirectly specified the probability law in our model by starting with conditional probabilities as opposed to starting with ordinary probabilities. Can we derive ordinary probability starting from the conditional ones? Yeah, we certainly can. Let's look at this event, A intersection B, which is the event up here, that there is a plane and our radar picks it up. How can we calculate this probability? Well, we use the definition of conditional probabilities, and this is the probability of A times the conditional probability of B given A. So it's 0.05 times 0.99. And the answer, in case you care, it's 0.0495. Okay, so we can calculate probabilities of final outcomes, which are the leaves of the tree, by using the probabilities that we have along the branches of the tree. So essentially what we ended up doing was to multiply the probability of this branch times the probability of that branch. Now, how about the answer to this question? What is the probability that our radar is going to register something. Okay, this is an event that can happen in multiple ways. It's the event that consists of this outcome. There is a plane and the radar registers something, together with this outcome. There is no plane.
Oh, okay. So we just add them up? No. I mean, we'll multiply 0.10 times 0.95 plus 0.05.
But the radar still registers something. So to find the probability of this event, we need to add the individual probabilities of the two outcomes.
That's what it said. That's what it fucking said.
For the first outcome, we already calculated.
Oh, shit.
For the second outcome, the probability that this happens is going to be this probability, 95%, times 0.10, which is the conditional probability of taking this branch, given that there was no plane out there. So we just add the numbers, 0.05 times 0.99 plus 0.95 times 0.1, and the final answer is 0.1445.
Yeah.
Okay, and now here's the interesting question. Given that your radar recorded something, how likely is it that there is an airplane up there?
That there is one?
Your radar registers something that can be caused by two things. Either there's a plane there and your radar did its job, or there was nothing, but your radar fired a false alarm. What's the probability that this is the case, as opposed to that being the case?
Same shit.
Okay. The intuitive shortcut would be that it should be the probability, you look at the relative odds of these two elements and you use them to find out how much more likely it is to be there as opposed to being there. But instead of doing this, let's just write down the definition and just use it. It's the probability of A and B happening divided by the probability of B. This is just our definition of conditional probabilities.
Oh, shit. Okay.
Now, we have already found the numerator.
Oh, shit.
We have already calculated the denominator. So we take the ratio of these two numbers, and we find the final answer, which is 0.34.
Wow.
Okay. Here, there's a slightly curious thing that happens in this example. Doesn't this number feel a little
too much?
Too low?
Too low.
My radar, so this is the conditional probability, given that my radar said there is something out there, that there is indeed something there. So it's sort of a probability that our radar gave the correct answer. Now, the specs of our radar were pretty good. In this situation, it gives you the correct answer 99% of the time. In this situation, it gives you the correct answer 90% of the time. So you would think that your radar is really reliable. But yet, here, the radar recorded something, but the chance that the answer that you get out of this is the right one, given that it recorded something, the chance that there is an airplane out there is only 30%. So you cannot really rely on the measurements of your radar, even though the specs of the radar were really good.
How the fuck does that even make sense?
What's the reason for this? Well, the reason is that false alarms are pretty common. Most of the time, there's nothing, and there's a 10% probability of false alarms. So there's roughly a 10% probability that in any given experiment, you have a false alarm. And there's about a 5% probability that something is out there, and your radar
entonces no es que no sea reliable, es que hay pocos aviones.
Gets it. So when your radar records something, it's actually more likely to be a false alarm rather than being an actual airplane. This has probability 10% roughly. This has probability roughly 5%. So conditional probabilities are kind of sometimes counterintuitive in terms of the answers that they get. And you can make similar stories about doctors interpreting the results of tests. So you tested positive for a certain disease. Does it mean that you have the disease necessarily?
No.
Well, if that disease has been eradicated from the face of the earth, testing positive doesn't mean that you have the disease, even if the test was designed to be a pretty good one. So unfortunately, doctors do get it wrong also sometimes, and the reasoning that comes in such situations is pretty subtle. Now, for the rest of the lecture, what we're going to do is to take this example where we did three things and abstract them. These three trivial calculations that we just did are three very important, very basic tools that you use to solve more general probability problems. So what's the first one? We find the probability of a composite event, two things happening, by multiplying probabilities and conditional probabilities. More general version of this. Look at any situation maybe involving lots and lots of events. So here's a story that event A may happen or may not happen. Given that A occurred, it's possible that B happens or that B does not happen. Given that B also happens, it's possible that event C also happens or that event C does not happen. And somebody specifies for you a model by giving you all these conditional probabilities along the way. Notice what we do along the branch as the tree progresses. Any point in the tree corresponds to certain events having happened. And then, given that this has happened, we specify conditional probabilities. Given that this has happened, how likely is it that C also occurs? Given a model of this kind, how do we find the probability of this event? The answer is extremely simple. All that you do is move along the tree and multiply conditional probabilities along the way. So, in terms of frequencies, how often do all three things happen, A, B, and C? You first see how often does A occur. Out of the times that A occurs, how often does B occur? And out of the times where both A and B have occurred, how often does C occurs? And you can just multiply those three frequencies with each other. What is the formal proof of this? Well, the only thing we have in our hands is the definition of conditional probabilities. So let's just use this. And
mira ese puto celular, huevón. Esto no fue 2010, esto fue 1920.
Okay. Now, the definition of conditional probabilities tells us that the probability of two things is the probability of one of them times a conditional probability. Unfortunately, here we have the probability of three things. What can I do? Well, I can put a parenthesis in here and think of this as the probability of this and that, and apply our definition of conditional probabilities here. The probability of two things happening is the probability that the first happens times the conditional probability that the second happens given A and B, given that the first one happened. So this is just the definition of the conditional probability of an event given another event. That other event is a composite one, but that's not an issue, it's just an event. And then we use the definition of conditional probabilities once more to break this apart and make it P of A, P of B given A, and then finally the last term. Okay, so this proves the formula that I have up there on the slide. And if you wish to calculate any other probability
this total theory problem.
This diagram, for example, if you want to calculate this
probability.
probability, you would still multiply the conditional probabilities along the different branches of the tree. In particular, here in this branch, you would have the conditional probability of C complement given A intersection B complement, and so on. So you write down probabilities along all those three branches and just multiply them as you go. So this was the first skill that we're covering. What was the second one? A intersection B complement, and so on. So you write down probabilities along all those three branches and just multiply them as you go. So this was the first skill that we're covering. What was the second one? What we did was to calculate the total probability of a certain event B that consisted of, was made up from different possibilities which corresponded to different scenarios.
The fuck?
So we wanted to calculate the probability of this event B that consisted of those two elements. Let's generalize. So we have our big model, and the sample space is partitioned in a number of sets. In our radar example, we had a partition in two sets. Either a plane is there or a plane is not there. Since we're trying to generalize, now I'm going to give you a picture for the case of three possibilities or three possible scenarios. So whatever happens in the world, there are three possible scenarios, A1, A2, A3. Mm-hmm. So think of these as there's nothing in the air, there's an airplane in the air, or there's a flock of geese flying in the air. So there's three possible scenarios. And then there's a certain event B of interest, such as our radar records something or doesn't record something. We specify this model by giving probabilities for the AIs. Mm-hmm. That's the probability of the different scenarios. And somebody also gives us the probabilities that this event B is going to occur, given that the ith scenario has occurred. Think of the AIs as scenarios. Okay. And we want to calculate the overall probability of the event B. Okay. What's happening in this example, perhaps instead of this picture, is easier to visualize if I go back to the picture I was using before. We have three possible scenarios, A1, A2, A3. And under each scenario, B may happen or B may not happen. And so on. So here we have A2 intersection B, and here we have A3 intersection B. In the previous slide, we found how to calculate the probability of any event of this kind, which is done by multiplying probabilities here and conditional probabilities there. Now we're asked to calculate the total probability of the event B. The event B can happen in three possible ways. It can happen...
Ok, puta madre, termino esto y... Y ya. Falta poco, mi hermano. Puta, dos videos para una clase, weón. O tres, creo. No, dos.
It can happen there, and it can happen...
Next chapter, we're gonna do fucking... We're gonna solve the problems. ¿Qué carajo es esto, weón? ¿Por qué lo estás haciendo así, weón? Un zigzag. The fuck? Sí. Ok, la wea simplemente es hacer esto. Vamos a tener... Vamos a tener que resolver eso. Ah, mira, quiero ver. ¿Cuántas paginitas? 2, 3, 4, y 5, y 6, y 7, y... Oh, network. Okay, here's where the good begins. Where the good stuff begins. Counting. Oh, not too much. Not that bad. 10 pages or so. Yeah. 9 pages. Not bad at all. Yeah. What about... Wow. 2, 1, 2, 2, 4. Let me see this. PDFs. Claro que sí, son PDFs. 2, 1, 2, 2, 4. No es mucho. Ni mierda, más bien diría. Piola, ¿no? Piola, piola, piola. Luego de eso, también pam, 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 pam. Parece que no es mucho. 2, 4, 2, 2, 5. Espera, 2, 4. Ah, chucha. Oñingo, 10 páginas. Ah, bueno, hasta 2, 6. ¿Cuánto es esto? 15 páginas aprox. Actually, yeah, 17 pages. Espera. ¿Qué carajo? No entiendo esta mierda. Ah, hasta el 2. ¡Carajo! Luego 2, 6, 2, 7. Ches. Bueno, 20 páginas casi, 18. Y luego ya, pues, hostias, ¿no? 3, 1, 3, 3. 18 paginillas. Bueno. Pero no está mal, no está mal, weón. Creo que podemos hacer esto cada, por día, ¿no? O cada 2 días, aunque sea. Recién te atacan, huevón, y ni siquiera has terminado, así que no te lo que es. I know, but... Sí, esto aquí es donde lo interesante, en verdad, empieza, yo creo. O lo cae de risa, no lo sé. Pause on process. Eso es just probability. Bueno, continuemos, mierda. Es que necesitaba un poco de dopamina, ¿no? Que es ver cosas nuevas, digas. Para motivarme. Estoy motivado. Caletado, chiquete que te pellao. Pau, chiquete que te pellao. Chiquelao, chiquelao,
Happen here.
Okay.
So this is our event B. It consists of
Say that shit again, Say that shit again.
In the previous slide, we found how to calculate the probability of any event of this kind, which is done by multiplying probabilities here and conditional probabilities there.
Yeah.
Now we're asked to calculate the total probability of the event B. The event B can happen in 3 possible ways. It can happen here, it can happen there, and
event B.
It can happen here.
What do you mean?
So this is our event B. It consists of 3 elements.
I don't get it. Ah, ya, porque puta madre estaba. Porque este es el complemento.
The total probability of our event B, all we need to do is to add these 3 probabilities.
Okay.
So B is an event that consists of these 3 elements. There are 3 ways that B can happen. Either B happens together with A1, or B happens together with A2, or B happens together with A3.
Okay.
So we need to add the probabilities of these 3 contingencies.
Claro.
For each one of those contingencies, we can calculate its probability by using the multiplication rule.
Claro.
So the probability of A1 and B happening is this.
A1 times... No.
It's the probability of A1 and then B happening given that A1 happened.
Oh, okay.
The probability of this contingency is found by taking the probability that A2 happens times the conditional probability of A2 given that B happened, and similarly for the third one. So this is the general rule that we have here. The rule is written for the case of 3 scenarios, but obviously it has a generalization for the case of 4 or 5 or more scenarios. Good. It gives you a way of breaking up the calculation of an event that can happen in multiple ways by considering individual probabilities for the different ways that the event can happen. Okay, so.
Oh my God.
Yes?
Does this have to change for infinite spaces?
No, this is true
Ahora
whether
que pone
the sample
micrófono,
space
weón.
is
Más
infinite or
lento.
finite. What I'm using in this argument that we have a partition into just 3 scenarios, 3 events. So it's a partition into a finite number of events. It's also true if it's a partition into an infinite sequence of events. But that's, I think, one of the theoretical problems at the end of the chapter. You probably may not need it for now. Okay, so going back to the story here. There are 3 possible scenarios about what can happen in the world that are captured here. Under each scenario, event B may or may not happen. And so these probabilities tell us the likelihoods of the different scenarios. These conditional probabilities tell us how likely is it for B to happen under one scenario or the other scenario or the other scenario.
Right.
The overall probability of B is found by taking some combination of the probabilities of B in the different possible worlds, in the different possible scenarios. Under some scenario, B may be very likely. Under another scenario, it may be very unlikely. We take all these into account and weigh them according to the likelihood of the scenarios. Now notice that since A1, A2, and 3 form a partition, these 3 probabilities have what property?
Additivity?
Add to what? They add to 1.
To 1, yeah, man.
So it's the probability of this branch plus this branch plus this branch. So what we have here is a weighted average of the probabilities of the B's in the different worlds or in the different scenarios. Special case. Suppose the 3 scenarios are equally likely. So P of A1 equals 1/3 equals to P of A2, P of A3. What are we saying here? In that case of equally likely scenarios, the probability of B is the average of the probabilities of B in the 3 different worlds or in the 3 different scenarios. Okay, so finally, the last step, if we go back again 2 slides, the last thing that we did was to calculate a conditional probability of this kind, probability of A given B, which is a probability associated essentially with an inference problem, given that our rate probability of this kind, probability of A given B, which is a probability associated essentially with an inference problem. Given that our radar recorded something, how likely is it that the plane was up there? So we're trying to infer whether a plane was up there or not based on the information that we got. So let's generalize once more. And we're just going to rewrite what we did in that example, but in terms of general symbols instead of the specific numbers. So once more, the model that we have involves probabilities of the different scenarios. These, we call them prior probabilities. There are our initial beliefs about how likely each scenario is to occur. We also have a model of our measuring device that tells us, under that scenario, how likely is it that our radar will register something or not. So we're given, again, these conditional probabilities. We're given the conditional probabilities of these branches. Then we're told that event B occurred. And on the basis of this new information, we want to form some new beliefs about the relative likelihood of the different scenarios. Going back again to our radar example, an airplane was present with probability 5%. Given that the radar recorded something, we're going to change our beliefs. Now, a plane is present with probability 34%. The radar, since we saw something, we are going to revise our beliefs as to whether a plane is out there or is not there. And so what we need to do is to calculate the conditional probabilities of the different scenarios given the information that we got. So initially, we have these probabilities for the different scenarios. Once we get the information, we update them and we calculate our revised probabilities or conditional probabilities given the observation that we made. Okay, so what do? We just use the definition of conditional probabilities twice. By definition, the conditional probability is the probability of two things happening divided by the probability of the conditioning event. Now I'm using revised probabilities or conditional probabilities given the observation that we made. Okay, so what do? We just use the definition of conditional probabilities twice. By definition, the conditional probability is the probability of two things happening divided by the probability of the conditioning event. Now I'm using the definition of conditional probabilities once more, or rather I use the multiplication rule. The probability of two things happening is the probability of the first and the second. So these are things that are given to us. They're the probabilities of the different scenarios, and it's the model of our measuring device, which we assume to be available. And how about the denominator? This is the total probability of the event B. But we just found that it's easy to calculate using the formula in the previous slide. To find the overall probability of event B occurring, we look at the probabilities of B occurring under the different scenario and weigh them according to the probabilities of all the scenarios. So in the end, we have a formula for the conditional probability, A is given B, based on the data of the problem, which were probabilities of the different scenarios and conditional probabilities of B given the A's. So what this calculation does is basically it reverses the order of conditioning. We are given conditional probabilities of this kind, where it's B given A, and we produce new conditional probabilities where things go the other way. So schematically, what's happening here is that we have a model of...
O sea, claro, pues porque mira, esta hueá es lo mismo. Probability of A given B. Yeah, it's this shit, right? Over B. Pero si esto lo traes acá, este es probability B times probability A given B, lo que sería BAP, o simplemente BAP, ¿no? BAP. Y aquí quedaría lo mismo acá, pues, ¿sí o no? En vez de BAP, BAP, sería ABA. ABA, la misma va. Entonces lo podemos revertir. Ahora esto, ¿qué carajo es esto? Lo mismo. Solo que no sé por qué B is the same thing. Is it? I don't know. Because the sum of everything.
Other way. So schematically, what's happening here is that we have a model of cause and effect. And so a scenario occurs, and that may cause B to happen or may not cause it to happen. So this is a cause-effect model.
Take a decision,
And
bro.
it's modeled using probabilities such as probability of B given AI. And what we want to do is inference, where we're told that B occurs, and we want to infer whether AI also occurred or not. And the appropriate probabilities for that are the conditional probabilities that A occurred given that B occurred. So we are starting with a causal model of our situation. It models from a given cause how likely is a certain effect to be observed. And then we do inference, which answers the question, given that the effect was observed, how likely is it that the world was in this particular situation or state, or which answers the question, given that the effect was observed, how likely is it that the world was in this particular situation or state or scenario? So the name of the Bayes rule comes from Thomas Bayes, a British theologian back in the 1700s. This calculation addresses a basic problem, basic philosophical problem.
A la mierda, weón. Puta madre. Puta madre, causa. ¿Qué fue, no?
Can learn from back in the 1700s.
Yeah, I didn't get this. The fuck is that?
And we want to infer whether AI also occurred or not. And the appropriate probabilities for that are the conditional probabilities that A occurred given that B occurred. So we're starting with
Are you really trying to explain me about this symbol? Integral symbol? Wait, what do you mean sum? That shit ain't sum. That shit is integral. Okay, maybe you have to explain it to me.
With a causal model of our situation, it models from a given cause how likely is a certain effect to be observed. And then we do inference, which answers the question, given that the effect was observed, how likely is it that the world was in this particular situation or state or scenario? So the name of the Bayes rule comes from Thomas Bayes, a British theologian back in the 1700s. This calculation addresses a basic problem, basic philosophical problem, how one can learn from experience or from experimental data in some systematic way. So the British at that time were preoccupied with this type of question. Is there a basic theory that we can about how we can incorporate new knowledge to previous knowledge? And this calculation made an argument that yes, it is possible to do that in a systematic way. So the philosophical underpinnings of this have a very long history and a lot of discussion around them. But for our purposes, it's just an extremely useful tool, and it's the foundation of almost everything that gets done when you try to do inference based on partial observations. Very well. Till next time.
Bees on the table. Bees on the table. We took 40 minutes to watch this shit. Okay. What page are we at right now? 46. Okay, we gotta solve this bit. But should we do it now? Oh my god. Okay, yeah. Let me fuck you, bro. Let me do one at least. Oh my goodness. Bees on the tail. Bees on the tail. Bees on the... Oh, actually, I actually did it. Because I'm a fucking genius, you know what I'm saying? Okay, that's what I did before watching the... or even reading the chapter, the book, whatever. So, first let me just see if I still have the same answer, because what the fuck is this type of answer, bro? It's just stupid. So, yeah, man, this is definitely not the answer. Peace on the table. Peace and niggas. Come on, bro. Come on, brother. Come on, brother. No. Come on, brother. Oh, fuck you, brother. Oh, that's alright. Okay. Okay. Let's go. Okay. Let's go. It's on the table. Look at that. If the forecast is rain, the probability of actually having rain that day is 80%. Okay, so how should I do that? PA. rain, right? The forecast is no rain, which means, oh, I'm a fucking genius. No, hold on. The probability of it actually raining is equal to 10%. I mean, shit. Oh shit, bro. Look at that. Fuck. Oh, you know what? I think. Come on, bro. I actually think this a conditional probability, right? This is the forecast. Rains. Actual rain. Right. During fall and winter, the forecast is rain 70% of the time. And during summer, the spring it is. And the spring it is 20% of the time. Okay. Wait. Oh, fuck you. Should we do. This should be like PC or something? I don't know. Maybe. Oh my god. Oh my god. Maybe. And during summer and spring is 20%. Okay, hold on. So this is the forecast is rains. And what it does. Wait. Come on, bro. Okay, the forecast is rains. And actually happens only 80% of the time when the forecast is rains. When the forecast is no rains, is no rain, I mean. Rains only 10% of the time. So what about the other 10% of the time? Well, the forecast is just. I don't get it. Oh, no, because those are different assumptions or conditions. Those are different conditions, right? Totally, yeah, because the forecast. So we can infer. Oh, that's what the professor was talking about, I think. So we can infer that did us, bro, like did us, bro. We can infer the when the forecast is rain, 20% is a lie, or Okay. Fall and winter, the forecast is rain 70% of the time. And during summer and spring, it is 20%. I think we can even do something like fall, winter, you know? Just put it C. I don't know. Training. And this should be another letter, actually, right? I don't know about this. Well, one day Victor missed the forecast and it rained. Fuck. Okay. What is the probability that the forecast was rain if it was during the winter? What is the probability for that the forecast was rain if it was during the summer? Okay. All right. So I think it's actually kind of easy. Yeah. Fuck. Missed the forecast and it rains. So he doesn't know the forecast. Oh my god. Forecast was rain, which is just this in the winter, right? Is it winter? During the winter. What's probably the forecast was rain? It was during the winter. What the fuck was even this? Okay, so they're saying every time I think, yeah, I think should be just, but I don't know how to prove it or what should be the fucking. Or should we actually add it? No, we cannot add this shit. Okay. Cause, cause you know, the probability. Wait, fuck you. Yeah. So during fall and winter, we at least 70% of the time we say it's gonna rain. From that 70%, we only fuck, I don't know what to say, acertar, huevón, atinar. But we are only right 80% of the time. So that does not mean that doesn't mean that we have to be right. No, yeah, we have to be right. Okay, but we only need to know that the forecast was rain. Fuck. Fuck you, man. I don't know. I was gonna say this, but I'm not sure, bro. And yeah, I'm gonna do the same. I mean, fuck. I'm gonna do the same here, but again, I'm not sure. What is the probability if the forecast was rain if it was during the summer? I mean, we don't use this either, so just multiply, I guess. Okay. Yeah, ranges. Just swipe across them. Okay. It's not just around a squiggly line. It is literally an elongated letter. Yeah, I know that. I know that. Yeah, I knew. Yeah, PDF, of course, not PDF. Probability density function. Wow, that's what we're gonna watch. I don't know. No, from the latter chapter. Alright. Gonna see that later. F of x instead we use a probability density function. Wow, cool, huh? F doesn't give you a probability, it gives you a height. Okay. You graph f of x, you get a smooth continuous curve over your sample space. Accumulated area. Yeah. Yeah. Yeah, definitely. The soul base rule. If the cause is definitely happening, what are the odds we see the effect? Right. Why it's easy? It's usually not hardware level. Hardware level? What do you mean hardware level? For example, the integration with the battery system. No, it's kind of got reliability. Given that the real multi-million-dollar military aircraft is in the sky, the radar dishes will successfully catch it and alarm 99%. Yeah. You have a good. Oh, fuck you. Which is 0.7? 0.2? No. Oh, which is, let me see. 0.7 and 0.2, yeah. When non-predicted. Oh, what the fuck? Shit. Actual rain, yeah. Forecast was rain. Wait, but this should be first here. This should be in the right. Oh, maybe not. Okay. Okay, let me see the time. Yeah, I mean, fuck you. Okay, I'm gonna take the little break. Then, yeah, we finish this bitch. We gotta finish this bitch. Alright. See ya.